to talk about proving identities today. So essentially, what we need to do is work with the trig identities that are given to us, which are the Pythagorean ones, the reciprocal ones, the sum and difference identities, and the double angle identities, to prove that other identities are true. And so typically what this involves is using the identities that we know to do substitutions and hope that at the end of the day, one side will sort of simplify to the other side. Okay? So just to make sure we know the difference between an equation and an identity, an equation is a mathematical statement that can be solved for one value of the variable, right? So, I'm having smartboard issues again today. Let me try this. Okay. This is true for specific values of a variable, okay? So for example, if we have 3x equals 15, this is true when x equals 5. Okay? And even if we have more than one variable, let's say we had y equals x plus 2. Okay? This is only true for specific ordered pairs, right? So yes, there are lots of solutions, but it's not true all of the time. It's only true, for example, let's say x is 1, y has to be 3. Okay? So this is true for example, you could say the ordered pair 1, 3, or you could say, let's say x is 10. That would be 10, 12, right, etc. But it's not like a free-for-all. It's not like we can pick whatever values we want for either of those variables and suddenly it's true. You set one, then you figure out the other. Okay? An identity is always true for all values of the variables. Okay? So for example, let's say we take a difference of squares. A squared minus b squared is always a minus b times a plus b. Or, you could switch those two around, but you'd get the same result. Okay? So that is an example of an identity. Okay? Verification versus proof. So verification is either numeric or graphic, where if it's a numeric verification, you're plugging in a value for all of the variables and making sure that when you evaluate, at the end of the day, the left side equals the right side. If you are verifying graphically, you graph each side of the equation separately as two separate functions and make sure that those two graphs overlap. Okay? Those are ways to verify. However, a verification is not a proof. Okay, so you have to show that for all values of the variable that the identity is true. Okay. Another thing that we need to think about with these identities is, I should say, it's always true for all values of the variable that are permissible, because with identities, you can have non-permissible values that crop up. And most of the time that happens because the only trig ratios that do not have a denominator are sine and cosine. And so often, if you're using any other sort of trig ratio, or if your identity has some sort of almost like a rational expression in it like this, then you are responsible for stating non-permissible permissible values. Okay? So if we are looking at this identity, you kind of want to look at one side at a time. And so what's nice right now is that the right side doesn't have any non-permissible values. okay? This is defined for all values of x. But on the left side, we see denominators. And we also see trig ratios that are not sine and cosine. So whenever you see that, you have to also state non-permissible values. Okay? So what I like to do is kind of convert everything to sine and cosine and then see where I'm at. And then based on the denominators that I see, I can get my non-permissibles from there. So I would take the tan x and write that as sine x over cosine x times cosine x over cosecant x is 1 over sine x. Okay? So from here, two non-permissible values emerge. Okay? So one of them is that cos x cannot equal 0. And the other one is that sine x cannot equal 0. And you have to then state what values of x would make this happen, right? So for cos x not equaling 0, x cannot equal pi over 2 plus or minus pi n, where n is an element of the whole numbers. And here, x cannot equal 0 plus or minus pi n, where n is an element of the whole numbers. Okay? And essentially, if you put these two restrictions together, what happens is that every pi by 2, you have a non-permissible value. So you could actually combine these into one. If we combine them, we would have x cannot equal 0 plus or minus pi over 2n, where n is an element of the whole numbers. And what's then going to happen is that you start at 0, and every pi by 2, essentially when you're on the axes, either sine will be 0 or cosine will be 0, you will have a non-permissible value. Okay? But a couple things that must be stated when you are working with non-permissible values. You have to be able to see the denominators. You have to state this piece. The whole denominator cannot equal 0, and then sort of solve for that non-permissible value. Okay? Another thing that he mentioned to me while we're on the topic of trig around the rubric and how it's marked. And I haven't actually seen this too much in this course, but in like 10C, you see it all the time. If you write cosine without writing cosine x or cosine theta, okay? If you do it once, they pretend it never happened. If you do that more than once, they deduct marks every single time, right? So if I said, for example, I don't know. The only example that I can think of right now is with the right triangle, because this comes up in 10C all the time. But if you had like a right triangle where this is x and this is like 2 and 5 or something, right? Something like that. So people in 10C do this all the time. They say cos equals 2 over 5, right? That's what I mean by leaving out the variable. Cosine means nothing unless it's attached to an angle. So you have to make sure that, and maybe just go through every single time you use a trig ratio, do you have a variable there? Okay, so that's what I mean. And then the other thing that he said about marking trig is that if you're working in degrees and you leave that little circle off, same thing. So if you do it once, they blink and pretend it never happened. If you do it more than once, you'll have marks deducted. Okay, so make sure you have those little tiny circles in there. That's not kind of those are not the kind of marks that you want to be deducted, because if you just kind of pay attention to detail, then you can make sure that you have that all checked off. One thing that you can do is do sort of that kind of check once you finish everything, so that you're only paying attention to that. Okay? All right, so we have our non-permissible values over here. Now we are going to prove this identity. Okay? And actually, before we do that, I have a space for us to write some strategies down as well in terms of how do we go about doing this. I think I'd actually like to start with that. Let's talk about some strategies. Okay? So the first thing that I would do when I'm looking at a trig identity, the first thing I have to decide on is which side am I going to work on, right? Sometimes we only work on one of them. Sometimes we work on both of them and get both sides to equal some other expression. But typically, if you're in that situation where you have to work on both of them, one side still needs way more work than the other one does, okay? So you got to pick which side you're going to start with. Typically, we start with the more complex side. Okay, so work on one side at a time and start with the more complicated side. Okay, so that's one thing. Second, you have to start to look out for, well, firstly, if you see anything other than sine and cosine, I would convert. So that's a big rule of thumb. Sometimes you don't need to do this, but I would say this always works. It always works for me, convert to sine and cosine. And then I would say there's a couple of things to look out for. You want to be familiar with the variations of the Pythagorean identity because that comes up all the time. Okay, and what I mean by variations is on our formula sheet we have sine squared theta plus cosine squared theta equals 1, right? That is one arrangement of that equation. You could isolate that for sine squared theta. Sine squared theta would be 1 minus cosine squared theta. Or you could isolate it for cosine squared theta. Cosine squared theta is 1 minus sine squared theta. And we see that substitution all the time. So I would say look out for the Pythagorean identity. Right? So for example, if you see 1 minus cos squared theta, or 1 minus cos squared x, this is equal to sine squared x, or sine squared theta, actually. Because, so that's a substitution that we do all the time. And in fact, I don't know if my mind was thinking about this previous problem, but you can see over here, one side is equal to 1 minus cos squared theta, right? So if we were to do any work on the right side, that's what I would do. I would replace that with sine squared theta, okay? So look out for that because it comes up all the time. And then the other thing is if you see any double angles, especially if there's a double angle on one side but not the other, use an identity to get out of that double angle situation, right? So like, for example, sine of 2a is equal to 2 sine a cos a. So try and move in that direction, right? So if you see a double angle, use an identity to get it in terms of the single angle. Okay, so for example, if you saw sine of 2a, right, on one side, but you don't see that 2a throughout, on the other side you just say a, then we need to go in the direction of replacing that with 2 sine a cosine a. That sort of thing. Okay? When we're proving identities, most of the time with the double angles, that's the direction we go in, is that we take steps to get out of that double angle situation. Okay? And then the other thing that I would, just as a tip, is if you don't know what to do, try something. If you find out that you're in a more complicated situation, than you started with, abandon ship, try something else, right? And that will happen a little bit as you work through these problems. And it's what you'll find is the more you do it, you start to get sort of hunches because you've been through the experience before. You've seen something similar. You've done a similar type of substitution. And so it doesn't seem, after you've practiced a little bit, like it's such a crapshoot as to where do I start, right? But it does feel like that at first, and that's normal. Okay? All right, so we are going to prove this identity. Now, on the right side, I'm going to do exactly what I talked about. And the only reason why I'm sort of starting here is because I already know, since we had that conversation, that's where I'm going. But this is equal to sine squared x, right? And just a reminder, maybe I'll write it up here. This right side is 1 minus cos squared x. The left side was tan x cos x over cosecant x. Okay? So I'm going to replace the right side with sine squared x.
Operator to the main gym, please. The facility operator to the main gym to help set up for the wrestling tournament. Thank you.
And then I'm going to leave that side alone. And in fact, on the left side, a lot of the work when you have to state non-permissible values, you have to go in that direction anyway. So I'm just going to kind of pick up where I left off over here with writing everything in terms of sine and cosine. So that I could see my non-permissible values. And I'll replace this tan x cos x over cosecant x with this. Sine x over cos x times cos x over 1 over sine x. Okay? And when I simplify, these cancel. So I'm left with sine x divided by 1 over sine x. So I'm taking a sine x, dividing it by a fraction. I can simplify that by taking that same sine x and multiplying by the reciprocal of the denominator. Sine x over 1. And that is sine squared x. So now we're at a stage where the left side equals the right side. Okay. Now, there's multiple ways to do this. I could have also completely just left this alone and then gotten down to the sine squared x, replaced the sine squared x on the left with 1 minus cos squared x. I've just proven the same thing. Right? Okay. Let's try another one. So algebraically prove each identity for all permissible values of the variable. State any restrictions on the variable. Yes?
Do you have like a completely blank page there? Like a
No, that was a mistake on my part. Yeah. Sorry. Yeah, I'm just giving you extra space. There you go. Okay. Algebraically prove each identity for all permissible values of the variable. State restrictions on the variable. Okay? So what I'm going to do first is, here's my identity. I'm going to set up a little chart, left side, right side. And a lot of the time, the first step is going to help you uncover your non-permissible values anyway, if they're not obvious. Okay? Now, the right side seems pretty simple to me, so I'm just going to rewrite it as is and probably leave that alone. Okay? So here's an example. Actually, if you just wrote sine plus cos and didn't write the thetas in, that's kind of what I mean. It's probably a better example than the one that I gave you earlier. Yes?
Does it matter if you replace all of the thetas with x's?
Does it matter if you replace them all with x's? So I wouldn't.
Just keep it like what the question is.
Yeah, but if you, like, you know, I would try and remember to be consistent with the variable given to you, but I wouldn't think it would be a big deal if you did that. I don't know, though. I can't say for sure. I can ask about that, because that probably, I'm sure, happened once or twice in, 10,000 exams. Okay, on the left side, I'm going to write all of this in terms of sine and cosine. So I've got 1 plus cotangent is the reciprocal of tan. So cos theta over sine theta over cosecant, which is 1 over sine theta. Okay? So where is my non-permissible? Yeah.
Sine theta for both.
Yes. Okay, so sine theta cannot equal 0, which means theta cannot equal 0 plus or minus pi n, where n is an element of the whole numbers. Okay? All right, so that's taken care of. All right, so what would you do next? Yeah.
Generally, the way I do it is I chuck, like, see cos over sine, I'll chuck that on the bottom. And then I go 1 over
Ooh.
sine. I kinda
Take
like,
this and put it in the bottom?
and then because it's 1 over sine theta, and I put that on the top.
Ooh, we can't do that though, because you're talking about moving a part of a sum down. You can't just move part of a numerator down to the denominator. Unless there's no sum there, which is kind of a hint as to where we're going. Okay? Ultimately, if you have stuff within fractions, you want to have single, single, and then you can multiply by the reciprocal. Yeah?
I think you have to get a common denominator.
Yes. Common denominator. Yeah. So the common denominator in the numerator is sine theta. So I'm going to multiply this guy by sine theta over sine theta times 1. And then what I end up with in the numerator, I have a single denominator here of sine theta, but then the numerator of that is now sine theta plus cosine theta. And in the denominator, I still have 1 over sine theta. Okay? And now I'm at a stage where I have, okay, fraction over fraction. I can take the first one, multiply by the reciprocal of the second. So I will have sine theta plus cosine theta over sine theta times reciprocal of this is sine theta over 1. And the sine thetas cancel. And so now we have that the left side equals the right side. Because all we're left with is sine theta plus cosine theta. Okay. Let's try another one. Cos x over 1 minus sine x equals 1 plus sine x over cosine x. Okay, so there's not much to do here in terms of converting to sine and cosine because we're already there. So let's just start with non-permissibles. Yes?
Sine x cannot be 1.
Yeah. Okay, so 1 minus sine x cannot equal 0, which means sine x cannot equal 1. Okay, and then the other one, yep. Right, cosine x cannot equal 0. Okay, now this guy will give, I didn't give myself a lot of room, but maybe I'll just do it down here. When sine x is 1, x is pi over 2. And that happens once per period. So for sine x cannot equal 1, we get x cannot equal pi over 2 plus or minus 2 pi n, where n is an element of the whole numbers. And for cosine x not equaling 0, that happens when x equals pi by 2 and 3 pi by 2. And that happens every pi. Okay, because, you know, this is like the x coordinate. So when is x equal to 0? It's at 0, yes. It's at 90 and 270, right? When x equals 0? Yeah. So here, x cannot equal pi over 2 plus or minus pi n. N is an element of the whole numbers. Now, in fact, this restriction for cosine takes care of the one for sine, right? It's more restrictive. So this is sort of our non-permissibles, because we're saying here it starts at pi over 2 but happens every pi. For the sine x can't equal 1, it also starts at pi over 2 but it's happening every 2 pi. Okay? And again, like I do want to sort of take you through, because I think a lot of you are still thinking in terms of the unit circle with these restrictions, which is totally fine. But my brain doesn't go there. I see it graphically. So there's my sine function. It's only equal to 1 once per cycle. So I know, okay, it's equal to 1. It's not going to happen for another 2 pi. Right? So this is y equals sine x. And then for y equals cos x, it happens twice when it's equal to 0 anyway, right? So here's pi by 2, and here's 3 pi by 2. And then it just keeps going. There's a space of pi here. So it happens every pi that it's equal to 0. Okay, so it's just another way of seeing things. And, you know, at a certain point, certain things will get tattooed to your brain. Maybe not this for you guys, but it is for me, right? Like I can just sort of see these. And for me, it's easier to see it graphically. When is it going to equal 1 and how often does it happen from the graph than from the unit circle. But again, there might be another teacher in this department who thinks about it differently, right? It's just sort of different ways of seeing the same thing. Okay, so we got our restrictions. Now here, like what are we going to do? It's all in terms of sine and cosine already. Yeah?
Would you multiply the conjugate?
Yeah, multiply by the conjugate, exactly. And where we're going to sort of be looking in terms of multiplying by the conjugate, and in fact, with this example, you could actually multiply by either conjugate. You could start with this one and work with the conjugate of the denominator, or start with this side and work with the conjugate of the numerator. But if we multiply by the conjugate here, this will now become 1 minus sine squared x. And that's equal to cos squared x. That's looking a little closer to that denominator, right? So that's sort of the big picture as to where we're going. But yeah, so if everything's in terms of sine and cosine already, you have to think about some other algebraic tools that we have, like the conjugate, like factoring. You might be able to factor something like that, okay? So I'm going to leave this side alone for now and work on this side. And I'm going to take the right side and I'll multiply that by 1 plus sine x over 1 plus sine x. Okay? And again, this is where a little bit of experience can help a little bit. You could, if you wanted to, distribute this in here, right? That would be sort of a logical thing to do. But I'm always kind of keeping my eye on the prize. I'm like, oh, I have a factor of 1 plus sine x there. I have that there. So I'm just going to leave it factored because my hope is that this will cancel out. Okay? If you had distributed it in, the cosine x in, that's okay. You can just factor it back out at the end if you need to. But if you can kind of look at the other side every once in a while and see, okay, am I seeing something that looks like the other side? Okay, let's just keep that where it is. Sometimes that can help. Okay? So I'm just going to leave the numerator as 1 plus sine x times cos x. Now in the denominator, I have, when I multiply this out, I get like a difference of squares. 1 minus sine squared x. Okay? So now what? Yeah?
The denominator is a variation of the neighbor.
Yeah. Denominator is part of that Pythagorean identity. So I can substitute, what can I substitute in for the denominator? Cos squared x, right? So 1 plus sine x times cos x. This is now over cos squared x. Okay? And then what? Yeah, you have a common factor of cos x the numerator and denominator. So this factor can cancel with one of those, and you're left with 1 plus sine x over cosine x. And you have that the left side is now equal to the right side. Okay, now, if we had done this the other way by multiplying by the conjugate on this side, we would sort of end up, it would be a very, very similar process. Okay, 2 more questions, and then we're done for today. All right, so prove that 1 plus sine x equals sec x minus sine x times sec x over cos x. Prove that this is an identity for all permissible values of x. Okay, so this is an important piece for all permissible values of x. So what do I need to look at to figure out those permissible values of x? Yeah, so you need to look at the non-permissible values, but you also need to pay attention to whenever you have reciprocal trig ratios, because there is a potential for another non-permissible value. Now, I don't think in this case it'll matter because sec x is 1 over cosine x, and that's already in the denominator, but it's something to look out for, right? So what I sort of do as a first step is, this is already in sine and cosine. I'm going to make this into sine and cosine, so I'll make it 1 over cos x minus sine x times 1 over cos x over cos x. And then I can see, okay, the 2 denominators that I seem to see is this one, 1 plus sine x and cos x. So I'm going to have from the first one, sine x cannot equal -1. And when sine x equals -1, that's actually right here. X equals 3 pi over 2. And it happens once per cycle, once per period. So this will give me x cannot equal 3 pi over 2 plus or minus 2 pi n, where n is an element of the whole numbers. And then I'll also have that cosine x cannot equal 0. And when cosine x equals 0, that starts at pi by 2 and happens every pi, right? So it's the same restriction we had before. X cannot equal pi by 2 plus or minus pi n, where n is an element of the whole numbers. And you could write these both down, but in fact, the second one covers the first one, right? Because let's say I added 1 pi to this, I'd get the 3 pi by 2, right? So really it's sort of this. Okay, now I think, now that that's taken care of, I'm going to start to work on this side a little bit. I'm going to leave this alone for now because it's already in terms of sine x. So I'll just maybe rewrite it, but then I'm not going to do much more there. Okay, what can we do here? Yep.
Multiply sine x by 1 over cos x, and then you get the same denominator.
Ooh. Multiply sine. Well, in the numerator, we actually already have a common denominator, don't we? 1 over cos x minus sine x over cos x. That's already, yeah, but that's a good idea. Let's simplify this so that it's almost like you want a single fraction in the numerator, right? So that's going to be 1 minus sine x over cos x over cos x. Okay, and I, at this stage, would probably simplify this so that it's not a complex fraction anymore, right? So this is like over 1. So take this multiplied by the reciprocal times 1 over cos x. And I'm going to run out of space here, but that will give me 1 minus sine x over cos squared x. Okay? So there's a number of things that you could do at this stage. You could continue on this side, or you might actually want to work on the other side and see if you can get the other side to turn into this, because that actually wouldn't be too difficult. Okay, let's say we continue with this side though. Where would you go from there? Yeah.
The cos squared x is the same as 1 minus
Yeah. We could actually go do the opposite substitution that we did in the previous question, because 1 minus sine x is a factor of 1 minus sine squared x. Right? So if I replace the cos squared x with 1 minus sine squared x, this can be factored. That's a difference of squares. So I will get 1 minus sine x over 1 minus sine x times 1 plus sine x. Right? And now we have this common factor of 1 minus sine x in the numerator denominator, so we can cancel that.
Isaac, can you please return to the gym, please? Isaac, return to the gym. Thank you.
And we end up with 1 over 1 plus sine x, which is the same as the left side. Okay, now just to show you that there's many ways that you could do this, you could also, let's say, I'm going to pull this up maybe below, but let's say we're at the stage where the right side rather, was, we had 1 minus sine x over cos squared x. Right, we were there, and then we replaced that with 1 minus sine squared x. Well, the other side is 1 over 1 plus sine x. So another option is to leave this guy alone on the right. On the left, multiply by the conjugate. See what that does, right? So we could also, this is like the alternate ending in a movie. Do this. And then on the left, you have 1 minus sine x over 1 minus sine squared x. And then you can replace the 1 minus sine squared x with cos squared x. And you have still left side equals right side. Okay. So there's multiple paths to victory. Okay. All right. You guys ready for the last question of the day anyway? Okay. All right, so prove the identity sine 2x minus cos x over 4 sine squared x minus 1 equals sine squared x cos x plus cos cubed x over 2 sine x plus 1 for all permissible values of x. Okay. So there's a lot that we can do here. So first, what are a couple of things that you can do? Because I know we need to address non-permissibles, but it's almost like you need to do a little bit of stuff first to address the non-permissibles. Yeah. Yeah. This denominator over here can be factored, right? And so on this side, we get that sine x can't equal 1/2. But when we factor this, we're going to get 2 possible x values, or 2 possible values for sine that it can't equal, right? So that's one thing that I would think about. And if you want to take it one step at a time, that is not always, sine of 2x minus cos x. Not a bad idea. And on the left side, we have sine squared x cos x plus cos cubed x over 2 sine x plus 1. Okay, so essentially what we see from this is that sine x cannot equal plus or minus 1/2, Can't be the positive or the negative. And so you have to think, okay, what reference angle has a sine of 1/2? It's 30 degrees or pi by 6. Now we have to apply that to all 4 quadrants because we have the sign being both positive and negative. So x cannot equal, okay, we're going to have to do it in 4 different things because we're doing the general solution or the general non-permissible values here. So the first one is pi over 6 plus or minus 2 pi n. N is an element of the whole. So that's the first quadrant angle. Second quadrant would be 5 pi by 6 plus or minus 2 pi n, where n is an element of the wholes. The third quadrant is pi plus pi by 6, so 7 pi by 6. And the fourth one would be 2 pi minus pi by 6 is 11 pi by 6. Right? And because essentially, visually, what it looks like is here's pi by 6. That has a sign of 1/2. It'll also be positive in this quadrant, where this is pi by 6. And then we also have the situation where sine is negative 1/2, which is over here and over here. Yes?
Could you do like just pi over 6 plus minus pi and then that kind of...
Okay, so I was thinking about that. I have to think through. I think what you could do actually is you couldn't just do it once. You could do this one and this one, and then switch the period to pi. Yeah, you can do that. Okay, yeah, that works. But it's also okay to do this and be a little bit redundant and make sure that you have it all there. That's fine too, right? Okay, so we took care of that. Whew, that's a big one. All right, what else can we work on? I think, to be honest, I can see some stuff in this question where I would want to work for sure on the left, but also on the right. So, you know what? Yes. Yeah, go ahead. Nope. Yeah, what are you thinking?
Sine 2x is, I think it's sine 2a. I don't have the, what's it called?
Yeah, this is a double angle. Yeah, right? So have that formula sheet out. Sine of 2a is 2 sine a cos a. So I'm going to do a substitution here so that I don't have that double angle in there anymore. And that will be 2 sine x cos x minus cos x over 2 sine x plus 1 times 2 sine x minus 1. Okay? So I'm kind of looking at both sides simultaneously and seeing some similarities. Yeah?
you could factor out a cosine.
Yeah, actually on both sides, right? On the left side, there's a GCF of cosine x. That's also true on the right. So you could work on one of these at a time, but I would do both, right? So we have here cos x times 2 sine x minus 1 over 2 sine x plus 1 times 2 sine x minus 1. So this is nice. These cancel. And that's quite simple. Okay, so at this point, I would stop on the left and start looking at the right and say, how can I turn the right side into the left side? Yep.
This is still... Oh, sorry.
You're okay? All right. So what can we do on the right side? Factor again. Yeah, exactly. Same thing, right? So we can take a cosine x out. And then from this term, we're left with sine squared x. And now I've taken one factor of cosine x out, but I'm left with 2. Yes.
The top would just be 1.
Exactly. now I see that Pythagorean identity. So this is just cos x times 1 over 2 sine x plus 1. And now I have that the left side equals the right side. Okay? So we're going to stop there for today. We're almost actually done this unit. It's pretty short. So the last lesson on this unit will be on Monday.